All right, go and take your textbooks out. Turn to page 417. Got a lot to review in 50 short minutes. So page 417, you had the homework section, numbers 1 through 9. You also had page 414, numbers 1 through 11. So we're going to start on page 417. 417. Put me in your textbooks. And the homework out. Quickly turning so we can go over this. Again, test will cover chapter 8, all things probability. Good. And then you had page 411, 1 through 11. Thank you. Or 414, 1 through 11. All right, there's the 1 through 9. There's the 1 through 11. If you would have your book open to page 417 so you can follow along there. Finding total number of outcomes. And frankly, we just multiply numbers together. Remember, it's called the counting principle, but we just multiply. It says each day for the next 5 days, one of 2 forklift employees will need to work extra hours to ensure products leave the warehouse on time. How many different ways could the situation play out? Well, every day you have another situation, right? So on day number 1, how many employees could stay after? 2. One of them will, right? There's 2 different guys. On the next day,
2.
On the next day,
2.
On the next day,
2.
And on the next day.
2.
So it's not that the 5 days are a choice. Each day presents a separate choice of 2. So we're going to multiply all of these together. How many different ways could forklift operators be the one to stay late? Class?
32.
32. Now, again, it might be, if it's Bob and Jerry, and let's go with Ben and Jerry, that sounds more. Anyway, if it's Ben and Jerry, it could be Ben. Okay, probably not. There's a 1 in 32 chance it's that way, but it could be Ben, Jerry, Ben. It could be Ben, Jerry. It could be Ben, Jerry, Ben. You know, I mean, you get the idea. There's 32 different ways you could construct that, because every day is another choice of 2. Number 2, for Science Club, the top 4 students will each present a project on one of the following categories: geology, microbiology, and ecology. So the first student presents how many different possibilities? How many different topics for the first student?
4. 3.
The first student could do 3 different topics, right? Then the next student could do 3 different topics. The next student and student number 4 could present 3 different topics. Because each student has one of 3 things they could do, right? You might get 4 ecology projects in a row. You might get geology, microbiology, ecology. You might get geology for all 4. There's how many different ways could these projects be presented? There are 81 different ways that the projects could be presented. So here, every student represents a choice. It's not that you're choosing one of 4 students. No. All 4 are going to do it, right? Just like all 5 days, Monday, Tuesday, Wednesday, Thursday, Friday, somebody's going to be staying late, right? It's just which of the 2 on Monday, which of the 2 on Tuesday, which of the 2 on Wednesday. Top 4 students are all going to present. Well, which of the 3 topics is that student going to do? Then the next student number 2 gets up, well, he's got 3 topics he could be doing. Then the third student gets up, which one of the 3 is he doing? And the 4th student gets up. So again, it's not that the 5 days are a choice. All 5 days are going to be there. It's not that the 4 students are a choice. No, the top 4 are already going to do it. It's just which choice are they going to do for each. Does that make sense how to set those up? All right. Number 3, a runoff at a track practice between 8 people will determine who will run each of the 4 legs in the next relay race. By the way, some terminology there, since I'm a track guy. A relay consists of 4 people. The lead leg is the first guy to run. He starts off with a baton in his hand. He runs a certain distance, and then he hands to the next guy. He gives him the baton, then he gets out of the way. The next guy runs whatever distance, and then he hands to the third guy, third leg, who runs, and then finally he hands off to the last guy called the anchor leg, okay, because he's the last guy to run. And so there's 4 spots up for grabs. How many guys want the 4 spots? There's 8 of them. Now, that means only 4 are going to get it, right? So, for the first spot, how many different guys could run lead leg? 8. There's 8 different guys. Now, once somebody's been chosen for lead leg, right, how many guys could be in the second spot? 7. And the third spot? And in the anchor spot? 5. Right? Typically, your fastest guy would go here and so forth. So, this is not a factorial, is it? It's a permutation. It's a permutation of 8 choose. Permutation of 8 choose 4, which means 8 times 7 times 6 times 5, right? The first 4 numbers in the 8 factorial, which means how many different possible relay arrangements can be formed?
1,680.
Good, 1,680. 1,680. Questions on that? Been a little while since we talked about permutations. Yes, ma'am?
I put the whole factorial in there.
But you understand, there's only 4 spots to fill. So after we filled the anchor spot, no more spots left, right? All right, take a look at number 4. A family has a 4-day vacation, right? So every day they're going to visit someplace. And there's 7 different places they're thinking of visiting. So on the first day, they're going to choose one of 7 different places. The next day, they're going to choose one of 6 places. They already went to one of the places. Then the next day, there are 5 places to choose from. And finally, on the last day of their vacation, there are 4 places to choose from. We would say this is a permutation, Lana, of 7 destinations. Choose 4 of them.
Yeah.
Permutation of 7, choose 4 is how we would write that. 7 places you could choose, but you're only going to end up going to 4 of them. And how many different ways could they spend their vacation?
1,120. That's what I got.
That's not what I got.
6 times.
Oh, that's why. 42 times 20. 42 times 20 gives us 840. Should have been our answer there. So again, maybe go back and brush up on the permutation chapter, the permutation section. And again, that's one of the upsides of doing this homework and of doing the review is you find what areas you need to brush up on tonight. As is typical, I give you no homework the night before a test, so that way the 30 minutes you would normally spend on homework, you can now spend studying just those sections you need help. You'll find sections, Lana, that you're like, I got this. Good, don't waste your time. This is a section probably need to go back and look over. All right, let's take a look at numbers 5 through 8. A child was playing with a wooden train set that included an engine, 6 coal cars, 7 box cars, and 2 tankers. No little red caboose. What is the probability that he would randomly select the engine and then he would pick a coal car without replacing? Now, technically, let's be real. What's the first thing you always have to grab if you're going to play with a train? You have to start with the engine, right? So technically, I would say experimental probability, there's like a 90% chance the kid grabs the engine first. But technically, theoretical probability, they're all mixed up in a box and he's blindfolded, he just grabs something. Okay, that's kind of what we're going off of here. What's the probability he grabs an engine, and then without putting it back, the next thing he grabs is a coal car? Well, am I going to multiply or am I going to add, class? I'm going to multiply because it says and. Now, are these independent or are they dependent? They are dependent because there's no replacement. So how many total things are going to be in the box of train cars? 16. I've got 16. I got 1, 6, 7, and 2 is 16 different things. Now, the engine is how many of 16? What's the probability of engine? 1 to 16. What's the probability of, now, he's already picked the engine, right? So there's now how many things left in the box? 15, of which how many are coal car? 6. So there's a 1 to 16 chance of engine, and then after that, there's a 6 to 15 chance of coal car. We could do a little reducing to cancel a 3 to get 2 and 5, cancel the 2 to get 1 and 8. So what is the probability, blindfolded, he grabs engine and coal car in that order?
1 to 40.
1 to 40. Did we get that for number 5?
No, because I just miscounted. I got 18.
So you had 18, 17 is your numbers there. So you had a 1 to 52 chance, plus your 2 to 52 chance. 1 to 26 chance, whatever that would be. I can't do math.
It was 1 to 51.
51. I'm trying to do math in my head. I'm not doing too good. All right, number 6. What about a coal car and then tanker? If the coal car is replaced, okay, do we multiply or add?
Multiply.
We multiply. Independent or dependent?
Independent.
Independent, because if he puts the coal car back and he pulls something out, coal car, tosses it back, blindfold, they mix it up, he reaches again. Well, there's still the same 16 cars. Now again, that your number's going to be off since you had 18. But so what's the probability of coal car? 6 to 16. Now, he puts it back in, so there's still 16 cars in there, of which how many are tanker? 2 tanker car. And so we reduce some things down to get 3 and 8 and 1 and 8, and we get
3
to 64. What about boxcar, boxcar, boxcar? No replacement. And there's 7 of them in there, right? But what's the odds he draws a boxcar, then another one without replacing? Okay, multiply or add? Multiply, because it's and. It's and in a row, right? And then independent or dependent? because he doesn't replace, it's very much dependent. So what's the probability of boxcar on the first poll?
7 to 16.
7 to 16. Then the next poll,
6 to 15.
6 to 15, because there's one fewer total, but it's also one fewer boxcar. Then the probability of the next one,
5 to 14.
5 to 14. And the odds just keep going, going down here. We can do some canceling. I really like that 14 because it allows me to cancel with the 7. I like canceling here, the 1 and 3, maybe canceling the 3 to get 2 and 1, and then the 2's canceling to get odds of
1 to 6.
1 to 16 chance of boxcar, boxcar, boxcar. So if you try 3 to 16 times, one of those theoretically, again notice theoretical probability, he would get boxcar 3 times in a row. What about engine, boxcar, or a tanker? Do we multiply or add? Add, because it says or. Now, are these mutually exclusive or not mutually exclusive? They are mutually exclusive. That which is an engine is not also a boxcar. And that which is a boxcar is not also a tanker car. I mean, even my kids know this when we watch the trains go by our house. It's like, if they're like, hey, that's a tanker car. No, that's a boxcar. Okay, it's both. No, there can't be both, okay? They're totally separate. They look nothing alike. So, what's the odds of engine? 1 to 16. Or means we're going to add, what are the odds of boxcar?
7 to 16.
7 to 16. Plus, what are the odds of tanker?
2 to 16.
So if I'm just like, I'd be happy with any one of those. What's the probability?
10 to 16 or 5 to 8.
Good. 10 to 16, which reduces to 5 to 8. Questions on that? All right. Number 9, finding mean, median, and mode. And for the mean, rounding off to the nearest tenth, what did you get for your answer, Joshua?
42 and 5, 6, which is 42.8.
Good, 42 and 5, 6, which is 42.83 repeating. But since it said the 10th, forget the 3 repeating. Let's just do 42.8. How about the median, Lana?
43.5.
Good, 43.5. 42 and 45 were both in the middle. Halfway between 42 and 45 is 43 and a half. And then the mode class?
No.
No mode. What mode? They're 1, 1. All right, questions on that? All right, so Joshua, other than getting the numbers right, good to go on the probabilities. And then Lana, do you feel like you understand these choice thingies a little bit better?
I was just thinking factorials and
Okay. All right, any questions? Flip back to page 414. We'll get a little bit more practice with both of those things here in today's review. Some quick questions, numbers 1 through 11 that you did here on page 414. Number 1, what is the term for the likelihood of an event occurring, class?
Probability.
Good, probability. Number 2, what is the probability of one event, or if the probability of one event does not influence the probability of another event, the events are called independent. And again, the only way to have independent is and. That's the only way, is that one occurs and then the next occurs, but the first doesn't mess with it. If it's this or this, the question is not independent, dependent. This or this is mutually exclusive or not, right? Is there overlap between the categories that you're pondering, either or? Number 3, in finding the probability of 2 events joined by or, you obviously would add. Number 4, why is that list not valid, Joshua?
Because it's not between 0 and 1.
Right, the sum, well, each one is, and that's really, each one has to be between 0 and 1, but the sum has to be exactly 1, and it's not. The sum is bigger than 1, so can't possibly be a set of probabilities. Number 5, all probabilities must be less than, Lana.
1.
What's the probability of something that is impossible? 0. How would I write out 5 exclamation point? First of all, how would I read it, Lana? 5 factorial, and we would get what when we wrote it out?
5 times 4 times 3 times 2 times.
Good, and did you happen to find the value by any chance? It'd be 120. It didn't ask for that. All right, number 8. What is the sum of 3 factorial and 4 factorial? Joshua? Number 8. 30. 3 factorial, 3 times 2 times 1 is 6. 4 factorial, 4 times 3 times 2 times 1 is 24. 6 plus 24 equals 30. Number 9. In which type of probability is each outcome assumed to be equally likely? I mentioned this already, Joshua. Theoretical probability. When, like we talked about, if the kid's not blindfolded, 90% of the time I'm betting, what's the kid grabbing out of the train set first? The engine. That's called, do you remember? Experimental probability. Excellent. What's a table that shows the number of observed results for each outcome? For instance, if we document it, all right, bring the kid in. engine. All right, thank you. You can go. Next person. Right for the engine. All right, thank you. You can go. And we just logged like 100 kids coming through. We're like, 90 of the 100 kids grabbed engine first. Mr. Nadasky was right. He's a prophet. Thank you. Thank you. All right, anyway. So if we just wrote down 90 kids grabbed the engine first, 2 kids grabbed the tanker car first, 5 kids grabbed the box car first, and I don't know, that leaves what, 3 for the oil car, if I'm keeping track right, or the coal car, whatever it was. If we just wrote down how many of everybody and added up to the total of 100, or maybe we brought in 200 kids or whatever, that's a lot of kids. Anyway, what do we call that table, Joshua? Frequency table. Now, if instead, Lon, I said 90% engine, 20%, well, they couldn't have 20%, 2% coal car, 5% box car. If I wrote down the percents, that wouldn't be a frequency table, that would be a relative frequency table. So very similar. One has the actual results, the other has the percentages, if you will, the relative frequencies or the probabilities. Questions on 1 through 10. Number 11, spinner on the right is spun 1 time. What is the probability of spinning a red area, Josh?
1 to 10.
1 to 10. How about a blue area, Lana?
1 to 2.
1 to 2. That'd be 5 to 10. 1 to 2. And then a white area, Joshua?
2 to 5.
2 to 5. 4 out of 10, but 2 to 5. Questions at all on the homework on that page. All right, number 12. T-shirt store has a kiosk where custom t-shirts are ordered. Each t-shirt can be red, blue, white, or yellow. 4 different colors. It could be plain or it could have a pocket. Also, they could put an animal, a personal photo, or a personal logo on the t-shirt. I guess you can't just have a plain t-shirt because you're going to have an animal, a personal photo, or a personal logo on your shirt. Whatever. I guess if you're going to get a plain t-shirt, you wouldn't go to a custom kiosk, because I guess that actually does make sense. How many different t-shirts could they make? How many different t-shirt designs? Find it. All right, how many colors were there?
There were 4.
4 colors to choose from. How many pocket or no pocket? How many choices is that?
2.
That's just 2, right? Yes or no. And then prints.
The prints.
2.
2. Wait, no,
Wait, what?
1, 4.
Oh, 3.
3, right? They could have a picture of an animal. They could have a picture of somebody, like a picture you give them, or a logo you give them, right? So that's 3 different prints. So how many different kinds of t-shirts could they make?
24.
24. Now that lumps all personal photos. I mean, technically, there's an infinite number they can make because you can have an infinite number of different photos. But like photo shirt versus logo shirt versus animal shirt, I guess 24 different types of shirts. Does that make sense? Again, each of those is a choice. You have to make a choice of color, choice of pocket, choice of print. On the previous problems we did for homework, the first student had to make a choice of topic, second student, choice of topic, third student, choice of topic, fourth student, choice of topic. Monday, they had to make a choice of which guy stays late. Tuesday, same choice. Wednesday, Thursday, Friday. The idea is figure out what are the types, how many different choices do you make? All right, now within each of those, how many different options are available to satisfy the choice? All right, number 13. A farmer in a local co-op will plant 1 crop from each category. For the first category, farmers can plant either corn or wheat. Second category, pumpkin, watermelon, or yellow squash. Third category, potato, carrot, parsnips? Anyway, I've never heard, well, I've heard of them. I have no clue what they are. Should probably look that up. How many different groups of crops can a farmer plant? Or just stay out of the co-op and be like, I'm going to do what I want, y'all. Terribly unsocialistic of me, I suppose. Free choice? What is this? This is America. You do what we say. All right, Lana? 18. Because category 1, 2 different things he could plant. Category 2, 3 different things he could plant. And category 3, another 3 different things he could plant. Gives us 18 different crop options that he could plant. Questions on number 13? Number 14, Todd's buying a gift card for his friend's birthday. First, he has to decide whether he's going to get an actual card or like an e-gift card, digital voucher. Then he's going to decide, okay, and once I figured that out, it's going to be food, always a winner, store, or digital service. I guess if you really like your phone, I like iTunes gift card. Anyway, then he's going to decide, do I give my friend $10 or 25? If it's another guy, $10. If it's a girl, 25. Anyway, not that she's actually impressed, but he thinks she is, so he'll do it. All right. How many different choices of gift card does Todd have? All right, Joshua? 12, because you got to make a choice of 2, then a choice of 3, and then a choice of 2, multiply to get 12. Questions on that? All right. Numbers 15 through 19. Number 15, 16, 17, you're going to show how to work out the permutation. Then for numbers 18 and 19, what is the permutation and what do we get for the answer? So 15, 16, 17, showing how we write it out and what's the answer. For 18 and 19, okay, what permutation are we even doing and what's the answer? Going to take a few minutes to do 15 through 19 there on page 415.
So we're not getting the answers for 15?
You're getting the answers for all of them, but on 15, 16, 17 specifically, the first thing they want you to do is actually write out all the numbers that you're supposed to use. And again, the only time you choose a permutation is when not everybody can be included, or not everything can be included, right? So there's 10 different things, but you can only pick 3 of them. Because if you could pick all 10, you just do 10 factorial. But it's pick 10, and you can only pick 3. How many different ways could you pick those 3? number 15. How did you write out a permutation of 10 choose 3? Joshua?
10 times 9 times 8.
Good, which equals?
720.
720. Good. Number 16. Permutation of 6 choose 4. Lana?
6 times 5 times 4 times 3.
Which equals?
160.
Ooh.
Well,
300.
360. 360. Some little carrying error probably. How about back to you, Lana, for redemption, number 17. Permutation of 25 choose 2. So we simply write out
25 times 24.
which equals?
600.
600. There we go. Number 18. Mrs. Munson has a display case for her collection of teacups. If the display has places for 5 teacups, how many ways can she display 5 of her 10 teacups? All right, so she's got 10 teacups. She's like, which 5 do I put up? This is similar, by the way. Okay, we got an open house tomorrow. So I've got a gazillion posters I could put up, right? So I'm like, I only really need a couple of them right now. So the extra ones I put up are really just for show, open house, look pretty. I was like, which ones do I put up? Okay, that's kind of what she's got going. I've got so many beautiful teacups and there's only room for 5. She could put up another shelf or just put up 5. How many different ways? Well, how do we write the permutation first of all, Joshua?
10p5.
10p5, and it's a pretty big number.
30,240.
30,240. 10 times 9 times 8 times 7 times 6 comes to 30,240. Number 19, Lana. A laundromat has 4 large capacity dryers and 8 customers waiting to dry clothes. I can just see the bloodbath about to ensue. How many ways can 4 of the 8 customers use the dryers? Lana, how would I write it in permutation notation?
8p4.
8p4, which is?
1,680.
There are 1,680 ways the customers could come out of that fight alive.
What was the answer for 18?
18 was 30,240. Did you have 10p5?
Yeah, I just didn't. I multiplied 10 times 9 times 8. I put 10p5, but then I.
You didn't take the first 5 numbers. You stopped at 8, you said?
No, I stopped at 7.
Okay, 10, 9, 8, 7,
Yeah.
6. We needed the 6 as well. Gotcha. Okay. All right. Questions on that? All right, we got some probabilities here. I want you to do 20 through 24, 2 bags of marbles. I don't need you to label dependent, independent, multiply, add, but you need to at least think it. You don't have to write it. 20 through 24, at your seats. All right, let's take a look at these. Number 20. What's the probability you get a red marble, then you get a green marble without replacing the red marble? Josh?
2 to 15.
2 to 15. Good. Number 21. What's the probability you get a marble that is not green from each bag? Lana?
7 to 20.
7 to 20. Good. Number 22. What's the probability just from the first bag you get blue or green? Joshua?
3 to 5.
3 to 5. Number 23. What's the probability you get a red marble, then you get a blue marble from the second bag with replacement? Lana?
3 to 50.
3 to 50. What about 2 green marbles in a row from just the second bag without replacement? Joshua?
2 to 9.
2 to 9 is correct. Anyone go 5 for 5?
No, because for some reason on number 21 I got 3 to 5.
Just on 21. So you got all the residues just 21? All right, let's take a look. Marble that is not green. Okay, so the first bag, from each bag means first one and second one. So we're going to multiply. Did you multiply?
Well, I just took like everything that wasn't green from the first one and then everything that wasn't green from the second one.
Did you multiply or add?
It's like I put 12 over 20.
Ah, okay, yeah. So we reach in the first bag, because that's the first thing that happens, right? We reach in the first bag and we pull out, come on, not green, not green. I just don't want green. Yay, it wasn't green. Then we reach in the second bag. All right, come on, not green, not green. So in the first bag, not green would be 7 to 10 probability, right? And in the second bag, not green would be 5 to 10. And we've got to multiply those, or we could say 1 to 2, and that's where we get 7 to 20. Does that make sense?
Yeah.
So we're not adding them to get 12 to 20, multiplying them. All right. Any other questions? 21 or 20 through 24. All right, do 25 to 28 now. 25 through 28. let's take a look at these. Number 25. What's the probability of drawing 2 good cards in a row from the first stack without replacing the first card? Lana?
33 to 95.
Good, 33 to 95. Number 26. What's the probability of getting either a good card or a great card from the first stack on a single draw? Joshua?
3 to 4.
3 to 4. Pretty good chance you're getting a decent card. Number 27. What's the probability that if you draw 1 from each stack, you get a great card each time? Lana?
1 to 20.
1 to 20. What's the probability of getting a good card or better from the first stack and then from the second stack? So, or better means good or great, right? So you either get good or great from the first, and then you also get good or great from the second. So that's what that means. And what do we get for that probability, Joshua?
1 to 4.
1 to 4 is our answer there. You need help with that last one, Lana?
Yeah.
All right, so in the first stack, there are 20 cards. And there are 12 good, 3 great, so 15 cards you'd be happy with, right? You don't want a useless card, so just not useless, all right? 15 to 20. And then you want, so times, you want a good or better card from the second. Well, there aren't any good, there's just great cards. So 5 out of 15 from the second one. Cleanly cancel the 15s, cancel, get 1 and 4, and of course that's your probability, 1 to 4.
On number 27 though, I got it right, but
You're not sure how?
how would you know if it's addition or multiplication?
Well, because to get a great card from each stack, it's not a great card from either stack, right? That would be either great from this or great from this. But it says from each, meaning you've got to get a great from both of them or a great from this and from this. So you have to mentally put the word and in there. When it says each of them, that must mean both of them together and the one and the other. Make sense? All right, good question. Good. Any other questions on 25 through 28? All right, do 29 and 30.
We already did that.
Oh, you already did 29 and 30, that's right. I had you work those in a previous lesson. Okay, good. Then that gives me time to go on to the last thing I wanted to work with you on, and that was not mutually exclusive events. Now, we had a quiz several lessons back, you'll recall. Remember? And on the quiz, we had not mutually exclusive events, and we didn't do great because we didn't think about it, right? So, remember, not mutually exclusive means there's some overlapping categories here. So, let's see here. Let's suppose, for a moment, that in the school, let's run some things down here real quick, because we're a real small school. We've got 7 7th graders, right? And that would be 5 girls and 2 boys, right? And now, technically, we've got 3 8th graders, but Scott, since you're not with us, we're going to say 2 8th graders who are physically on campus. We've got a girl and we've got a boy. And in 9th grade, we've got 3, well, technically 2, because your brother isn't here either, Scott. So 2 9th graders physically on campus, 1 girl and 1 boy. So let's suppose I wanted to choose somebody to help me with something. What is the probability that I either pick a boy to help me or I choose a 7th grader? A boy or a 7th grader to help me? Well, how many boys are there?
2.
No, how many boys are there?
4.
There's 4 boys in the 7th through 9th grade, right? So 4 boys out of how many total kids in 7th through 9th grade?
11.
11. Or means I'm going to add. How many 7th graders do I have?
7.
7 out of
11.
11 people. However,
Overlap.
there are some boys who are 7th graders, so we have to subtract those who fall into both categories. How many fall into both conditions?
2.
The 2 7th grade boys, so we have to subtract them away. And so really our probability of me either choosing a boy or a 7th grader is
9 to 11.
9 to 11. Does that make sense? What if I said the probability of picking a 9th grader or a girl at your seats? The probability that I pick a 9th grader or that I pick a girl. All right, probability of ninth,
2
2 to 11.
probability of girl,
7 to 11.
but there is a ninth grade girl. So we have to subtract her away
1 and 2 11.
because we can't have her counting toward both categories is the idea. So what's the actual probability?
8 to
8 to 11 that I pick a ninth grader or I pick a girl. Does that make sense? What about the probability that I pick a boy or I pick a girl? Don't overthink this. Because we should already know the answer. What else would I pick?
Oh!
So what's the probability?
1.
1. Of course I'm going to pick. And by the way, these are mutually exclusive, by the way, right? There's no overlap between these, right? I mean, you could take the time and be like, let's see, 7 girls, that's 7 to 11. 4 boys, that's 4 to 11. I see the overlap. There's no overlap. So it's 11 to 11. Oh, that's 1. Boy, of course it's 1. Okay, how about this? What about the probability I pick a 7th grader or an 8th grader? What about the probability I pick a 7th grader or an 8th grader? All right, what's the probability of 7th?
7 to 11.
8th?
2 to 11.
Is there any overlap?
No.
No, because if you're in 7th, you are not in 8th. There's no overlap, so we just get
9 to 11.
9 to 11. That makes sense? All right. Do we understand the overlap thing? When something can fall into both categories, that's when we have to be concerned with overlap. So, again, girl doesn't preclude you from being in 9th grade. Oh, you can't be in 9th grade. You're a girl. No. Or 7th grader? Nah, you're not a boy. You're in 7th grade. Like, what? Those are not mutually exclusive, but wait, you're a girl? Oh, then you're not a boy. Right, amen. You teach some scientists some things here. Anyway, questions on this? Questions on this? All right, any questions at all as far as the test is concerned? Let's skim back in our books very quickly. Go all the way back to page numero 364. Okay, that's where all of this material begins, with basic probabilities, right? For our purposes, always be written as a ratio or a fraction. Okay, that's what we're going to be doing even on the test tomorrow. Remember the complement, that's not a term that came up yet, right? That's the probability something does not happen. Probabilities have to be between 0 and 1. We'd already talked about that. Remember the counting principle, you just multiply all the different outcomes from each choice. So, look at that first example there, bread, meat, cheese. 2 breads, 3 meats, 3 cheeses. Okay, well that's 18 different things that could be. Permutations. How many different ways can things be rearranged? Now, if everybody gets to be included in the arrangement, just a basic factorial. Well, otherwise, if you're going to pick only a certain number, that's where you use that permutation. Flipping, mutually exclusive. Remember that or means add, assuming that there's no overlap. And then in the level up, we talked about not mutually exclusive. Subtract away the probability of both. So some stuff there. Independent events. The first event doesn't mess with the second. Just find their probabilities. But then we talked about dependent events. You have to account for it when you change the denominator and maybe even sometimes that numerator. As you work with those, you multiply the ands. From there, we went to mean, median, mode, measures of center as we work with data and statistics. Remember, with outliers, if there's big outliers there, we would want to use which measure of center as our main one? Median. Okay, if there aren't really any major outliers, then the mean is a good measure of center. And of course, if it's not numeric, if it's categorical data, the only thing you could use would be mode. But I suppose sometimes mode can be a good indicator even with numeric data. Remember the dot plot, that little kind of a graphy type thing. We talked about theoretical probability versus experimental probability. I think we've got, let's turn over to page 416 now, page 416. And we've got a little frequency table there with bracelets and necklaces and rings and watches. Remember, for a frequency table, you just write in all the numbers, right? 100 watches, 30 necklaces, 50 rings, 60 bracelets. You'd have to add them all up, right, to get the total. And then if you wanted to find the relative frequency, what would you do?
It's like
You would-
divide.
Right. So for instance, there were 60 bracelets. If you were to add them up, you get 240 total. Total. But here, instead of leaving it as 1 to 4, we'll generally make it decimals. So 0.25, meaning there's a 25% chance that people would pick a bracelet based on past history. Again, people aren't walking into a store and reaching into a grab bag, right? They're walking into a store making a conscious choice, what do I want to buy? So, if you're the jewelry store clerk, you're going to make sure you have plenty of watches, because that's what most people are buying. You're really not interested in stocking a whole bunch of necklaces. Nobody's really buying those. So that's where relative frequency tables come in. However, when you add up all the relative frequencies, what do they have to equal?
1.
They have to add up to 1 because that's the total probability. Okay, questions on that? All right, no homework this evening. Have a wonderful rest of your day, and we'll have that test tomorrow in our next lesson.